Hazardous waste are poisonous byproducts of manufacturing, farming, city septic systems, construction, laboratory, hospitals, and other industries. The waste may be liquid, solid, or sludge and contain chemicals, heavy metals, radiation, dangerous pathogens, or other toxins. Even household generates hazardous waste from items such as batteries, used computer equipment, and leftover paint or pesticide. The rules surrounding hazardous waste are overseen in the U.S. by the Federal Environmental Protection Agency (EPA) as well as the state departments of environmental protection. One shocking fact is that the U.S. didn't think about managing its toxic waste not until 1976, and that was the year when EPA began regulating hazardous waste around the country. One EPA rule that has been controversial around the country was allowing sludge containing heavy metals to be included in fertilizers that are used by farmers on food crops or sold directly to the public. Environmental and other organizations say dangerous levels of the metals are taken up by some plants and subsequently eaten by people, with particularly negative effects on children. Stimulated by advances in microbiology, the environmental biotechnology field focuses on the use of microorganisms to treat or degrade hazardous wastes, such as bioremediation, biodegradation, microremediation, etc. All of these methods depend on the ability of particular microorganisms to synthesize the enzymes needed to break down complex toxic compounds into intermediate compounds or individual elements. Let's look at these methods up close. Bioremediation, its concept involves using organisms that either naturally love to eat contaminants or have been genetically altered to give them the taste for toxins. Scientists are designing or deploying microbes to purge sites of contaminants such as PCBs, oil, radioactive waste, gasoline, and mercury. Some of you might ask, how do we determine what organism is suited for what pollutants? Well, an associate professor of environmental technology at Louisiana State University, Ralph Portier, has successfully identified more than 400 different microorganisms, and the waste products still degrade. He has managed to do this by creating tiny environments for the naturally occurring microbes. To each of these environments, he adds a specific pollutant. Then, one by one, he removes different components of the environment until all that remains is toxins and the microorganisms. The microbe that can live off the pollutants will thrive, whereas those that can't will die. Some of the microbes Portier has identified through this method has been used to degrade pollutants such as chlorinated phenols, pesticides, hydrocarbons, and heavy metals found in contaminated soil. According to the European Environment Agency, heavy metals and mineral oil are the main soil pollutants. One of the most popular techniques that tackles this problem is phytotechnology or phytoremediation. Certain plants have a particular gift for sucking up specific chemicals. When these plants are sown on contaminated ground, they absorb the contaminants into their tissues, gradually reducing the amount in the soil until it is safe for humans. Some of these plants known for phytoremediation are Indian mustard. It can remove 3 times more cadmium than others, reduce 28% of lead, up to 48% of selenium. It is effective against zinc, mercury, and copper as well. Another plant would be sunflower. It reduces different polycyclic aromatic hydrocarbon level from soil in an effective way, but what is really surprising is how varied range of contaminants they can accumulate. Heavy metals such as lead, zinc, phosphorus, potassium, cadmium, copper seem to be its food, which is great news because sunflowers have a quick growth to start working soon. In fact, 1-month-old plants reached an incredible goal of removing more than 95% of uranium in 24 hours, which shows their power to remove radioactive metals, including cesium and strontium, from superficial underground water. Recently, low-cost absorbents developed from natural material or certain waste material from agricultural or industrial activities to reduce the heavy presence of toxic metals in aquatic environments, for example, walnut shells, dried tree leaves, rice hulls, chicken feather, dairy manure, sawdust, and corn cobs had shown excellent sorption capacities for toxic metal ions from solution. In a current study, tea waste has been selected as an absorbent of three toxic metal ions: lead, cadmium, and copper from aqueous solutions. Sorption behavior of lead 2, cadmium 2, and copper 2 onto tea wastes were evaluated in terms of the influence of solution pH, sorption kinetics, system temperature, and solid particle size. The short useful life expectancy of electronic products, driven by rapid innovation and affordability, have led to a major increase in the accumulation of toxic electronic waste. Increasing recycling rates is a central strategy for dealing with the e-waste problem, as well as reduction in the use of toxic materials and designing for easier deassembly and resource recovery. Only a small fraction of e-waste generated in the US is recycled, whereas there is evidence of exportation to developing countries such as China and India. Most countries are at the early stages of developing environmentally sustainable solutions to deal with e-waste. However, the processes that they use often lack pollution control measures and excessive levels of toxicants that are released into the environment. Past adventures of some advanced nations like Switzerland, Germany, and Sweden demonstrated that consumer participation should be cultivated to facilitate e-waste collection, which can be stimulated by economic compensation and promoting moral norms, educating the public about the benefits of collecting e-waste and making e-waste collection more convenient, but other measures will likely be necessary to tackle this problem.